Alright, so let's continue the tutorial 5 here. And we're going to, this is a very important topic, which is defining your own functions. I've color-coded this to make this as easy as I can to understand, but let's look at the structure. What we're going to do is we're going to define a new function, f, and when you define a new function, well, we need to bring in all the aspects of syntax that you need to define a function. When you have a function, you need to know what its inputs are, you need to know what its outputs are, and you need to know the rules to get from the inputs to the outputs. And I suppose we could also say you need to know what the name of the function is. So let's go through each of these bits individually. So we're going to create a new function called f. If you want to make your function longer, you should always make it use maybe the same type of structure as a Mathematica command, which is to use alternating lowercase, uppercase letters to start the new words. All Mathematica functions and predefined commands and special characters all start with an uppercase letter. So it's often good practice to start your functions with a lowercase letter. As before, every function in Mathematica requires square brackets. This is no different. It's going to mark the beginning and the ends of the inputs. Inside these square brackets, you give your names to what the parameters are, what each of the input, when the user provides numbers or arguments into your function, you need to catch those, and you're going to give these the local variable names. So x and y here represent the variables that catch the inputs of the function. The underscore here is an important part of the function. So what this underscore is doing is it's telling Mathematica that what's being put into this function satisfies a pattern. This single underscore here is just saying the input can be anything. We'll learn more about patterns later on in the course, but this is the simplest version of a pattern. And so when we see x underscore, what that is saying is the input can be anything. It can be of any type of input. So the last thing that you'll notice here that's different from what we've seen before is this construction of a colon equals. And we're going to talk about that in a second here. The way you can read it is set delayed, and the brief explanation is it's only going to evaluate the right-hand side after you provide the information. Let's ignore that for right now. What we're doing is we've now know what the inputs are. There's two inputs to this function, and so in order to completely define what the function does, you need to fill out what the right-hand side is. And that's going to depend on what you want your function to do. Alright, so let's do a couple of simple examples. Here's a very simple example. Let's define a function that takes as input a number and outputs its square. Alright, so what we need to do is we need to create a name. So we'll call me square me. We need a bracket, and then we have some inputs, close bracket, and then colon equals, and then the rule. So the input here that we have is there's just one number that's input, and the output is that number squared. So if we evaluate it, so before this is evaluated, notice that this is blue. Square me is blue because it has not yet entered into Mathematica. when we evaluate it, it becomes black, and all future versions of square me become black because now Mathematica knows what square me means. And so if we apply this square me to -6, that's going to take this -6, it sees -6 as the x, it squares that value, and that's what the output is. It gives out 36. One thing you'll notice here is that every input that you put in here becomes teal, right? It's actually not the same teal as the like the table or the in the table command or some of those other commands. This is actually a more green than teal color. So it's telling you, this is helpful because let's say we were to evaluate this without the underscore, that's going to be some clue that something's not right. The color here is no longer this greenish teal. Instead, it's blue because x hasn't been defined. So this is another instance where Mathematica is giving you some visual clues about your function, about your syntax. Let's do another example where we have two input variables. So here's an example where we have a function, and what we would like the function to do is to take two inputs and output the sum of those two things. So this here we're defining add 'em up, and add 'em up takes in two inputs, which we're going to call x and y. And the rule on the right hand side is to take x plus y. And so once we evaluate this, we can apply it to 3 and -10. Now you might be thinking, hey wait, don't we have the total command that does that? Well, let's look at total. If we were to plug in 3 and -10, that doesn't do what we thought it might do. And that's the key reason for that, is that the total command, if you remember, takes as input a list. So when we write total 3, -10, this is not the same syntax as add 'em up, because add 'em up always takes in two inputs and outputs the sum of them. Alright, so if you'll notice here, add 'em up will do this for any inputs. So if we do add 'em up of this list and this list, it will add up these two vectors. If we add up red and orange, well, we get red plus orange. And if we add up hello and goodbye, we get hello and goodbye. Now Mathematica has put them into whatever format it wanted because these are strings, and so goodbye comes before hello, so it put them in that order. But this is the sum of two strings. So this function that we've defined is a completely general function no matter what the input for x is, no matter what the input for y is. So now let's do two examples. Excuse me. The first example says, define a function that takes as input a number and outputs that number plus a random integer between -5 and 5. Alright, so what we need to do is we need to create, let's call it random noise. And we need to have an input that's a number. So why don't we call it n? And we'll do colon equals. And you'll notice, I guess before n was defined, but because we're now putting n underscore, this is now a local variable that's only defined inside random noise as the parameter that will be replaced when this function is called. And so what we want is we want the output of this to be n plus a random integer. Now luckily there's a function called random integer, and let's look at the syntax of this. Information, random integer gives a pseudo-random integer in the range from imin to imax. Random integer needs a list with two numbers in it. So in this case, n plus random integer from -5 to 5. So this is now the function. It takes in a number n, and the output is n plus a random integer from -5 to 5. Now this, let's check to make sure this works. Random noise of 100 should give us some number that's between between 95 and 105. We run it one time, 98. Run it another time, 101. Every time we run this, it's a number between 95 and 105. All right, so now let's look at this next example. We've created a function, and we want to take the function we defined and apply it to all the elements in the list from 1 up to 100, and then create a scatter plot of the result. So there's a number of pieces to do there. Let's take them one at a time. We created a function random noise, and we want to apply it to a list of a whole bunch of things. Hey, that sounds like something we did earlier, which is to use the map function. So what we're doing here is we're saying random noise. We want to map this function onto the list of numbers from 1 to 100. The list of numbers from 1 to 100 is defined by range of 100. And so now what we have is we have a list of numbers where each of them is created by taking the number 1 or 2 or 3, etc., and adding a random number between -5 and 5 to it. And then to create a scatter plot of this result, well, that's a list plot. And list plot, let's just use the shortcut for the previous output. And here we go. And this is what we might expect to see. We might expect to see them lying along a line where there's some noise from that line. Now that I'm thinking about it, another nice example, let me draw in one more example here. So example 5.3.3, what we can do is we can say modify the random noise function to allow for a second variable that tells us how much noise to add. A second variable that defines how much noise should be added. All right, so let's do that. So what we want to do is we want to take this random noise, and we want to, instead of being from -5 to 5, let's instead make it, we have n is the number, and then we have another variable for noise, and we'll make it be from negative noise to positive noise. And so if we look at this and we say random noise of 100, but we allow ourselves to have a range of 100, what that's going to do is it's going to add plus or minus 100. So some random number between plus or minus 100 and to this noise. All right, so that's enough here. We will continue in a second.